Ladies and gentlemen, this is the second part of our chapter on mechanisms of plastic deformation, and now we are going to talk about dissolution creep. Dissolution creep is also commonly known as pressure solution or as dissolution precipitation creep, which describes in broad terms what is actually happening during this process. What is important for dissolution creep to work is the presence of a fluid phase, which is typically contained along grain boundaries and in the pore space of rocks. And into this fluid phase, some of the rock material is dissolved once a differential stress is applied. We see that here on the right hand side. If we apply a differential stress field onto a porous rock, we will find that there are stress concentration at the interfaces where individual grains are in contact with each other, and the stress concentration in these places will facilitate dissolution into the fluid phase present nearby. Once the fluid phase is oversaturated with cations, a precipitation process might take place that could fill open pore space, but also could form other structures such as lenses of precipitated mineral material or hydrothermal veins that form from oversaturated fluids. Minerals that are very commonly affected by dissolution creep are quartz and calcite, and accordingly veins that we find, hydrothermal veins that we find, are very commonly quartz or carbonate veins, and some contain both phases. The precipitation is not restricted to veins and layer parallel lenses. We also might find in strain shadows of rigid crystals precipitated quartz. Very commonly we find that in garnet or staurolite bearing rocks. Garnet and staurolite are high shear strength materials, and in their strain shadows we often find wings of precipitated quartz. An important feature of dissolution creep is that it is not volume constant, because when we dissolve material at these high stress areas, we will shrink the volume. The pore space might get closed when the individual grains change their shape, and we might squeeze out fluids that are enriched in the dissolved material that is now missing from the original volume. That means, in contrast to the deformation mechanisms that we have previously discussed, dissolution creep is not volume constant. We see that here when we look at the reference circle that is representing the initial undeformed state. We do form deformed minerals, typically stretched minerals with a maximum stretching and a maximum shortening direction. But we also see that the strain ellipse occupies a smaller area than the initial circle that represents the strain-free situation. Here we see a similar graphical illustration of the same process. You apply a directed stress field, a differential stress field, along the contact surfaces, particularly those that are perpendicular to the maximum principal stress. Dissolution will be most intense, and the dissolution into the fluid might lead to precipitation of the same mineral phase nearby, or the extraction of the fluid into other places, such as hydrothermal veins. In nature, we observe that different mineral phases have different solubility and high solubility. We particularly observe in minerals with ionic bonds, such as the salt minerals. Halite, for instance, has a very high solubility. Even at very low temperatures, it will dissolve in groundwater. Carbonate, similarly, is highly soluble at low temperature conditions. When we look at the silicates, that is different. Quartz, for instance, pretty much all silicates are dominated by covalent bonds, which are much stronger, not easy to dissolve, but in hydrothermal fluids there is a substantial solubility of silicates, and quartz has the highest solubility of the common rock-forming silicates. Micas and amphibole and pyroxene and garnet have a comparatively much lower solubility, and that has consequences about the effects of dissolution creep on common crustal rocks. Let's make a little thought experiment. Let's assume we look at an undeformed rock with a certain content of a mineral phase that has a low solubility, such as white mica, for instance, shown in orange here, in a matrix with a mineral that has a much higher solubility, such as quartz. If we expose this rock to a differential stress field in the presence of a fluid phase, we will find that a part of the quartz will dissolve, SiO2 will be enriched in the hydrous fluid that is present, and that will remove a part of the quartz content in the rock. If the fluid is extracted into perhaps hydrothermal veins, this will cause volume loss. And not only this, it will also change the whole rock composition of the rock, because the mineral phase that is unaffected, that has lower solubility, will become relatively enriched. And in this case, in our example, that would be the mica. After dissolution creep has taken place, the rock has lost a part of its quartz volume and then will become more enriched in the mica. At the same time, the mica crystals will move closer together and perhaps form continuous foliation planes, and that will pronounce a foliation that might have been weakly developed prior to the deformation process. This works also if the distribution and the orientation of mica is irregular in the undeformed protolith. Once we remove the quartz during dissolution creep, these individual mica crystals will start to rotate into a uniform direction and form a mica-rich foliation. The importance of dissolution creep is that it is already effective at relatively low temperatures. At sub-greenschist facies and lower greenschist facies temperatures, quartz and mica-rich and carbonate-rich rocks will undergo a quite intense dissolution, and at these conditions, the only other deformation process that might take place is fracturing and faulting. For processes of plastic deformation, the temperature is too low. Only from about 300 to 400 degrees plastic deformation becomes important in silicate-bearing rocks. In carbonates, that threshold temperature is quite a bit lower. As soon as we exceed the lower to middle greenschist facies temperature conditions, plastic deformation in quartz-rich rocks becomes faster and more effective and eventually dominates the structures that we see. However, dissolution creep will stay active as long as there is a fluid present that can dissolve minerals that are present in the rock. In quartz or carbonate-rich rocks, dissolution creep can have a substantial impact on the whole rock chemistry, because it will relatively increase all other minerals that are less or undissolved and remain behind during dissolution creep. And if alignment of these minerals takes place, schistose rocks will appear through dissolution creep. And most foliations that we see in common pilitic or samopilitic rocks in the crust initially will have been generated by dissolution creep. The conversion of micaceous quartzite into mica schists is also a feature that is also a process that often is not recognized. In greenschist facies rocks, also amphibolite facies rocks, many people interpret mica-rich rocks as initial metapelites. That is not necessarily so. There could be samopelites from which a large part of the quartz component has been removed during the prograde evolution in presence of hydrothermal fluids by dissolution creep. Here we see an example how plastic deformation in combination with dissolution creep can affect the nature of rocks. The protolith that we see here in this example is clearly a granitic rock. We see here in this part of the image a fairly undeformed part. Also here a number of large feldspar crystals that apparently still have their initial magmatic shape. We also don't see strong foliation planes in these areas, but as soon as we approach this mylonite zone that we see here with a very intense foliation, we see that all magmatic structures have been overprinted. A transitional stage between the less or undeformed protolith and this mylonite we see at the top of this image here. We see a strongly stretched out alkali feldspar phenocrysts that form these lenses and are well aligned into a foliation plane. We also can see that the rock starts to develop a very pronounced foliation, indicated by aligned mica and aligned feldspar lenses. But the deformation intensity is much less in this upper part compared to the mylonite or ultramylonite that we see here in the center, where very few feldspar lenses are still recognizable at the scale of observation. We see also here that the high strain zone is splitting up and some thinner, less intensely deformed mylonites are branching off to the bottom of the image here. This is a typical feature of strain partitioning that we will find in greenschist and amphibolite facies conditions. This appears to be an amphibolite facies shear zone because we see significant plasticity of feldspar, which takes place only above a threshold temperature of about 500 or 550 degrees. Typical sinks for dissolved silica in hydrothermal fluids are, of course, hydrothermal veins. We see here a beautiful hydrothermal vein in a metasandstone in a quartzite from the Cape Fold Belt. Here we see anertional tension gases. These are also examples from South Africa. These are the typical sinks for dissolved SiO2 during dissolution creep. We can assume if we see these kinds of features in metasedimentary sequences that dissolution creep was an important process. Even more important is this process if the protoliths contain finely distributed commodities that can be dissolved in the fluid phase. For instance, gold is often associated with hydrothermal veins, and the dissolution creep and the concentration of the fluid phase along vein systems very often upgrades the gold content so that it becomes an economic ore resource. At the microscale, we might also observe evidence of dissolution creep. Here, for instance, a thin section from a deformed rhyolite. These rhyolites contained euhedral quartz crystals, and part of the euhedral shape is preserved. We see here euhedral boundaries there, also here, here, and here. But some edges are dissolved into a fluid phase. We see that here indicated by the arrows, and where we find these dissolution surfaces, we also see a concentration of undissolvable material, mica most likely in this example, which is more strongly concentrated in these areas where dissolution creep had taken place. In carbonates, we often observe stylolites. Also, stylolites are related to dissolution creep. And in carbonates, the phase that is undissolvable is typically graphite. Stylolites are these irregularly shaped, strongly serrated fronts of dissolution, along of which the undissolvable graphite is concentrated and then forms these blackish serrated lines and surfaces in 3 dimensions that are often observed in marbles, in low temperature marbles that were affected by dissolution creep. If we summarize the distribution of different deformation processes in diagrams that show differential stress and temperature, we find the predominance of different fields at different conditions. A schematic diagram here on the left-hand side shows that at various differential stress conditions and low temperatures, dissolution creep is important as a process, provided that a fluid phase is present. Otherwise, mechanical twinning is possible for some minerals such as calcite or some feldspars. If the differential stress is sufficiently high, the rock will break and undergo cataclasis. With increasing temperature, more diffusion-dependent processes become possible. The first one would be grain boundary diffusion creep, which works at relatively low and moderate differential stresses and temperatures sufficiently high for diffusion in the present mineral species. With higher temperature, volume diffusion becomes possible as well. But we should not forget, as long as fluid phase is present, also at these high temperatures, dissolution creep will play its part in the deformation process. And also grain boundary diffusion creep does not stop just because volume diffusion creep becomes possible. Dislocation glide and dislocation creep are more typical for higher differential stress conditions. They start at moderate temperatures and become more and more effective with increasing temperature. Dislocation creep here shows a very typical decrease in differential stress with increasing temperature, simply because the diffusion of cations becomes more effective at increasing temperatures. On the right-hand side here we see two strain maps specifically drawn for quartz and calcite. They look very similar, like the schematic one that we see here, that in principle applies to all mineral phases. We see here fields for dissolution creep. There are temperatures given. They refer to the results of certain experiments. You can look up more detail in Davis and Reynolds' textbook, chapter 4. And we see here again at high differential stresses, 100 to 1000 megapascals, dislocations glide becomes possible, taken over by dislocation creep. Volume diffusion creep is shown here at low differential stresses and high temperature. Grain boundary diffusion creep was not observed in these experiments. Similar for calcite, we see at lower temperatures, dissolution creep is the only dominant and important deformation process. Increasing temperature allows the diffusion-related processes to become active. We see contour lines on these diagrams here. They refer to strain rates. Strain rates are measured per second in a logarithmic scale, and the smaller the number is that we see indicated here, labeling these different contour lines, the slower the deformation rate would have been during the experiments that were carried out and from which these strain maps were produced. So I believe this covers the most important information on dissolution creep and the other deformation processes, those related to plastic deformation. Thank you very much.